Morning, everyone. Can you hear me okay at the back? Cool, awesome. Yeah, it's good to be here and good to have you all here. I hope you're all vaguely awake still. I know I'm not. So a lot of today is about reinforcement learning, which is a field very dear to my heart, and I hope it will be to yours too soon. Okay, so just a quick rundown of what we're going to talk about today. First, I'd like to tell you a little bit about what reinforcement actually is. I think this is quite important because people typically familiar with supervised learning and unsupervised learning, and reinforcement learning until quite recently was always the kind of illegitimate cousin in the corner. And recently it's become a big deal. Now you can go to conferences and sit in reinforcement learning tracks for an entire week. Before it was one little session that was snuck in the middle somewhere. We're then going to move on to talk about several different types of methods. Now, there's a huge plethora of methods in reinforcement learning, and I think even including the talk that will follow ours, we're just going to touch on some of the main ideas, give some examples of the kinds of methods you can work with to try to get some of the general intuitions across. So in particular, we're going to look at 3 classes of methods, focusing mainly on value-based methods, and then also talking about model-based methods, and also policy search, and we'll show how these different ideas tie together. And then we're going to talk a little bit about inverse reinforcement learning and some of the applications of reinforcement learning. There's this thing. Okay, so as I said, we've seen a lot of cool problems over the last few days, mainly around supervised and unsupervised learning, and all sorts of interesting techniques to solve them, obviously mainly tied into deep learning techniques. So there's different kinds of classification problems and regression problems that you all should be quite familiar with and comfortable with after the lab sessions particularly. But actually, a major component of intelligence is decision making. And that's something that we haven't spoken about much yet. The reinforcement learning actually aims to address this problem. And this is the branch of machine learning that is all about making sequential decisions. In some environment, you want to repeatedly make different decisions over time. And you can think of this in a sense as learning behaviors. So to compare this to something like supervised learning, there you've typically got one decision point, right? So let's say you've got a deep net of some sorts. You can have some input data, and you really want to make a decision. And that decision might often be in the form of trying to classify, to go with the example everyone uses, is this a cat or a dog in this image, right? That's a single decision you're trying to make. But actually, we might be interested in many cases in what happens over time. What happens if there's multiple decisions that we want to take? And this isn't just a case of scaling up what we were doing before. There's other desiderata we have to think about. For example, how do you know if you're doing the right thing, right? If I did something 10 minutes ago, how do I know how that's contributed to something good that happens to me in the future? If you're playing a game of chess and you win the game, how do you know what actions you took during that game that led to a positive outcome? Or maybe you lost. What actions led to that? It could have been that you played badly the whole time. It could have been that you made a critical mistake. Now, these are important things to think about. In addition, your decisions actually affect the future, right? If I take an action now, I'm somewhere different to where I was a second ago. And this is going to affect the way you plan and change the way that the dynamics of an environment roll out over time. So it's not just a trivial extension from what's been happening before. So the setup looks something like this. You have some sort of decision maker, our little robot here, that's living in some environment. And we'll talk a little bit later on about how this needn't just be a robot, but let's go with this example for now. And also in the field, we typically refer to our decision maker as an agent. So if I start mentioning agents, that's what I'm talking about. Now, what's going to happen is at each time step, your agent is going to take some action. And we'll refer to those as A. And the action that you want to take depends on the state of the environment. And again, we'll talk about that in a bit. Now, once I've taken an action, 2 things happen. Firstly, the state of the environment changes. Now, this might be something about where I am and what I'm doing. If I move part of my arm's now in a different configuration. If I pick something up, its position relative to the rest of the world has changed. In addition, I get some reward. I don't always get some reward, but I can. And what this does is this gives me some idea of how good is the thing I've just done. For example, you might get a reward of 1 for winning a game of chess and -1 for losing it. And this is really how you get feedback to your environment. So this could almost be thought of analogously to your label in a supervised learning setting, although it is different. Now, before we go much further, we need to introduce some notation. Now, the most common setting for reinforcement learning is to work on what are called Markov decision processes. Now, this is a stochastic process that describes the interaction of this agent, this robot, with its environment. And typically, it's referred to with this 5 tuple. And that's the definition of an MDP, a Markov decision process. I'm just going to go through what these terms stand for. So first, you have states and actions. So as I said, the state represents the configuration of the world and the configuration of the agent within the world. And this should model everything that you care about. Now, your actions are the choices you can make. And you can think of this conceptually as you might have some set of states in an environment, and in each state, there's actions you could take. These may be the same actions in different states. Your action set may change. But for now, let's keep it at the same actions happen everywhere. We then talk about this term T, which refers to the transition function. And this tells us how the world evolves. This says, if I'm in a particular state and I take a particular action, what happens next? Right? This encodes the fact that standing here, taking a step sideways, moves me over here. And these can be deterministic, so sometimes an action might take you with full 100% probability to another state, but not necessarily, right? This could encode all sorts of different processes. Now, we typically model this as a probability distribution over successor states, so that's the state at time t plus 1, given the state at time t and the action at time t. I'm in a state, I take an action, and now, under some probability distribution, I move to another state. I haven't included past states here, and I'll talk about that in a second, but that's what you need to know. So the term we care about is T, S, A, S prime, which is a probability. Right. We then have this reward that is critically important because we can't learn anything without it. Now, this could come in as some sort of positive or negative number on some of these transitions. It doesn't have to be all of them, which is something very important. And here what we're looking at is that by being the feedback signal, we want the reward when you take a state, take an action in a state. Sometimes you can also model this as a state action state. What we're looking at is the expected reward in that configuration. So taking that action in that state gives me some reward. That reward could be drawn from a distribution, and that's what I care about here. Right. So that's something actually I didn't talk about. So we're imagining this process evolving over a number of discrete time steps. And you can think at each time step, I start off in state ST, then I take action AT, and then I move to ST plus 1. Okay, so that's if I am in state ST, and I take action AT, then I receive a reward RT. In this case, I haven't made it dependent on ST plus 1, but you could do that. Yes? It can be non-deterministic. So this is just the general formulation. There's a lot of special cases of this. I'm not putting any conditions on that at the moment. Oh, wait. I missed that. All right. Then we have this final term, which is a gamma, which is a discounting factor. And this, a bit of philosophical discussion about if gamma belongs in the definition of your MDP or not. But basically what this tells you is this gives you some sort of relative trade-off, and I'll talk about this more a bit further on, about the value of reward now versus reward in the future. So what gamma might say is that receiving reward R right now versus receiving reward R one step into the future, I discount that reward one step in the future. I multiply it by gamma, which is less than 1, so it shrinks gamma. And that means that that reward is worth less to me. Right? And we're going to use this to trade off the idea of immediate rewards versus future rewards. So finally, there's this idea of the system being Markov, and it's all in the name, really. Now, many of you may be familiar with this. The Markov assumption basically says that the future is independent of the past given the present. So what this means is when I look at, the notations is messed up there, but when I look at the state transitions, for example, I don't care about what happened 10 steps ago. So everything that I care about should be modeled in terms of the current state that I'm in. It doesn't matter how I got to this state. Now, remember that the state can encode any other information that I do care about. So there's ways around this. You can roll the history into the state. But basically, that's saying that I don't need to infer my future state based on looking at the whole past trajectory. So that just means I need to look very locally in time at what's just happened. OK, is everyone comfortable with that terminology? Right. OK, so I now want to just talk through a tiny little toy example. Let's imagine you've got this little cleaning robot, this little Roomba, running around some weirdly shaped room. There's some sort of obstacle in the middle. And it's looking for this dirt, and it doesn't want to fall into that hole, because it's a very weird room, because that's what computer scientists do for fun. Now, the way we're going to encode this is you've got a set of states, which is described by this. You've got a set of actions, which is that the robot could move one cell north, south, east, or west. We're then going to give it some rewards. So we're going to say it'll get a reward of +1 for finding the dirt. That's like a success criteria. -1 for falling into this hole. And in addition, every time it takes an action, it's going to get a tiny negative reward. Now, this is a trick we often use to make sure that our agents don't sit and waste our time. Right? If it could take a short path and a longer path, you want to penalize it in some way for using up extra energy. And that's what we're doing here. OK, so the states here, for example, could just be encoding each one of these cell positions. I described the actions, but let's start off by saying that the actions are deterministic. If I'm going to try and move north, then there's a 100% probability of moving in that intended direction, and that's where I'm going to end up. Right, so what does an optimal policy look like? Now, the policy is the behavior we're looking for. In this context, you can have a look, and these arrows very intuitively give you the direction that this robot should move in to perform optimally in this task. What does it mean to perform optimally in this task? We mean find that dirt, do it as quickly as possible, and don't fall in the hole. Right, so what we're looking for in this case is we want in each state, we want the direction drawn from that set of 4, the cardinal directions, of which is the preferred direction to move in each cell. Now, it turns out, even if you change this so that it's stochastic, so that I move in the intended direction 80% of the time and end up on one side or the other 10% of the time, this is still the optimal policy. You could also change that. So what if I'm just the most uncoordinated person ever, and if I'm trying to move north, I'll only end up there 10% of the time, and I could end up to either side 45% of the time. You get a very different kind of optimal policy. So you get something that looks like this, right? Now, if you think about it, what this is saying is if I'm trying to take a step in a particular direction, I'm more likely to end up on one of the sides. So if I'm trying to get there, I should try and move up, right? I don't want to move down because it might take me closer to this dirt. On the other hand, if I'm around this dirt, I definitely don't want to move anywhere that's perpendicular to it because I could end up there with a 45% probability. So this is just an illustration of how your behaviors that you're looking for are going to change depending on the dynamics of the environment. Obviously, if I change the rewards, then the policy is going to change as well. If I move the dirt around or if I move the hole, then all of this will change as well. So practically, we don't always just want Roombas to clean rooms. I mean, most of us do all the time. But there's a number of interesting problems you can solve with this. Towards the end of the talk, we'll go through a number of different application areas. But just take a different example where you might be trying to treat a disease in someone. And in particular, let's look at like a chronic disease. So maybe you can't actually treat it, but you can manage the symptoms. So you can think of a number of cases of conditions that you might want to do something like this. But the point is, it's not a single decision event, right? This person might be going back to the hospital at some regular interval, and each time there might be some different intervention we want to try. Now, your state information in this case could include all sorts of things, right? So you might have some background information about this patient, demographics and family history and so on. But then you might get some test results that tell you what's actually going on in their body and talk about this kind of the prognosis and progression of the disease. And particularly, you might see something like this. So you might have, over time, there's some underlying, say, wellness factor or their condition, and this might be fluctuating up and down as a function of this condition, and perhaps we can take measurements at certain intervals given by this red line. And the point is, at certain points, I might want to apply different treatments. And at each one of these different time points, there's a different decision I want to make. And obviously, whatever I do at one point is going to affect the future. If I apply something, it might make things better or worse, and that might change what I do the next time this person comes in. So what we really care about here is trying to find the best treatment strategy. And again, that ends up looking like a robot cleaning a room at the right level of abstraction. So something important we need to do is be able to evaluate these trajectories. Right? This robot could walk around falling into holes all the time. It might zoom around collecting all the dirt. I need to have some way of saying that one is better than another. And fortunately, we can do this using the rewards. And in particular, what we're going to do is we're going to look at the total discounted accumulated rewards. So as it goes about its trajectory, it's going to accumulate a whole lot of rewards. We're going to discount them into the future. And we're going to use this, a single scalar number, to say that some trajectories are better than others. Now let's talk about these rewards a little bit. Now, there's a lot of intuition that's come into this field. In fact, the whole field itself came from this idea of reinforcement learning in psychology, where get people to do things by hitting them with sticks or giving them carrots. And that's really what we're doing here, except for an artificial agent, a carrot is a +1 and a stick is a -1, which is, I feel less bad about that. As I said before, we're working with a scalar feedback signal, which really isn't that much information, right? You could take an entire trajectory and get a +1 at the end of that. That doesn't tell us a huge amount. But what our reward does do is it encodes what is desirable and isn't desirable here. So as I mentioned, with, say, the chess example, you can encode winning and losing. You could encode collisions with objects. And you could also penalize taking expensive actions. So some sort of cost for, as I showed in the previous example, you could have this cost for taking every action that you take. Now, the important properties that we care about here is, firstly, it's a sparse signal. So again, for 80 actions, I might get one little piece of feedback. It's typically delayed, again, in that at the end of this trajectory, you might say, well done, and well done what? And importantly, it's the relative value that's important in this context. So you can scale these things up and down as much as you want, but you're usually looking to optimize this, so you want the best actions in each situation. I just want to tell you a little story about the Rats of Hanoi. In the early 1900s, when Hanoi, I think, was under French rule, and they started putting in sewer systems. Turns out rats really like sewers. And when they did this, they had this huge explosion of rats in the city. They were everywhere. They completely filled up the sewers, and then they started spilling over to the surface. Now, this was obviously a problem. There's bubonic plague and all sorts of delightful things like that. And the kind of guys running the city had to do something about this. So first they went and got a bunch of rat headhunters, whatever those might be, and they were down there getting rid of these rats by the thousands, but it wasn't enough. The rats were still, the population was growing uncontrollably. So they decided, all right, cool, let's crowdsource this problem. So they went to their citizens and said, all right, we want you guys to take care of the problem because there's a lot of you and there's a lot of rats and we can't do this ourselves. And so we want you to go and kill the rats, and we'll give you 1 cent for every rat that you kill. But we've thought about this. We're not stupid. We don't want piles of rat corpses like filling up the tax offices or something. So what we're going to do is you're going to bring us the rat tails. from every rat that you kill, and we'll pay you for that. So this worked really well. Like, the whole population caught onto this, and soon they were getting bucket loads of these rat tails. Until one day they noticed that not only had the rat problem not stopped, it had gotten worse, and there were an awful number of untailed rats running around the city. Turns out what people were doing is, first of all, they were, why kill a rat when it's going to make baby rats? And baby rats can make other baby rats, and you can chop all their tails off. Why would you kill it? So you just collect its tail. And in fact, people started rat farms. So this is just a little anecdotal story about how it's a little bit difficult to specify reward functions. And anybody who's worked in any company anywhere will know this, particularly if it's in government. And it's really hard. You come up with these awesome incentive schemes, and you find they're misaligned. And people abuse these ideas and find their loopholes, and they hack the system, and you get really crazy unintended consequences. Now, this is a big problem with reinforcement learning as well. You might often find that you very cleverly encode the system where you have your agent, and you say that, all right, I'm going to give you a reward of 10 for getting to the door and leaving the room. And then it comes up with this crazy elaborate trajectory to do that. And you say, oh, I get it. I didn't penalize you for taking actions. All right, I'll give you -1 for every step that you take. And then it doesn't move. You say, okay, what's going on now? And you realize, oh, it was 11 steps away from the door. So by not moving, it was actually doing better than if it had walked to the door. Right, so this is a problem that you have to think about a lot when designing reward functions. And this is a very difficult problem. Okay, but once we have a reward function, then we can go and look at policies. So a policy or a behavior or a strategy is any mapping here from states to actions. So this is the thing that we care about. This is the thing that tells you, what do I do in each state? Again, this can be deterministic or stochastic, but we normally model this as some probability distribution over your action space conditioned on the state that you're currently in. And what we're really looking for here is the optimal policy, the policy that beats all other policies. Right? So this is the one that maximizes your total accumulated reward for any trajectory that you run. Now, I alluded to this earlier. There's a difference between kind of immediate future rewards and longer-term rewards, and this is something humans are ridiculously bad at. Now, you could say, oh, I could just take a one step and get some reward, but if I took a different one, I'd get nothing. Now, it turns out that's not the whole story. And rewards don't encode everything that we care about, because it might be that if you've headed off in that direction for 5 steps, you would have gotten a much bigger reward. And I'm sure you've all got examples in your own life where you've done this badly. We do use discounting to try and say that a reward in the future is worth less, and that's because there's some uncertainty. You're not guaranteed to get it. But you shouldn't just act myopically all the time. Don't take the best action just based on what reward will give you in the next time step. And so what we really want here... So when I'm talking about this, just imagine that it doesn't know that. It just knows, let's say, a one-step look ahead. And we'll talk about those different cases later on. So if reward isn't telling us everything, it's just telling us what's happening now, and we want to know what's happening in the future, we need some other notion for this. So we're going to talk about this notion of value. And that describes how good a state is, or an action in a state, if you're looking into the future, right? Which is really what we want. We want to make optimal decisions based on how things are going to roll out from here. And we're going to represent these as a value function. So what is a value function then? That's exactly what I just said. So we want to know what is the expected return, starting at a state, and then following a policy. I mean, a particular state, I want to know the value of that state. And the value, importantly, is defined under a policy, right? So if I'm trying to get to the door, this is a pretty good state. If I'm trying to take over the world, I don't know if this is a great state, right? So it depends on the policy you're trying to execute. And here by reward, I mean accumulated return, looking into the future. And so mathematically, this is what we get. We have the value of a state under a policy is going to be this return, which, as I said, is the accumulated reward if I've started in this state, and it's the expected value of that under some policy, under this policy that we care about. So what that means is that we're going to look from the current time step all the way into the future, until the ends of the earth, and we're just going to sum up all the rewards at each one of these transitions I'm going to take, importantly, under that policy, And we're also going to discount it by gamma. So the further in time it is, the more discounted it's going to be, right? Because I've got less chance of actually reaching that. It's going to look all the way into the future. It's essentially saying we want to look, if I just ran this policy for the next 10 years until it ended for some reason, how much reward will it have accumulated? And the intuition here is you're just asking, if I have this policy pi, how good is this particular state? Sorry? Well, it's under a specific policy. So you're going to look at the possible outcomes that are going to come out of this, and that's why we're looking at that expectation. So that expectation is going to give you an average over all trajectories that could have come up under this policy. So let's just think of this as a definition for now. There's different ways you're going to use this. Ultimately, what you want to do is learn this information. If you did have all that knowledge of its environment, you could just compute this directly. Otherwise, you might need to actually interact with your environment to get this information. All right, so let's look at a very simple example of this. Imagine you've got this little 5x5 grid world. And again, we can move in cardinal directions. But for every step that I take, I'm just going to get a reward of -1. Now, I've got two magic states that are teleporters. So if I arrive in state A, I'm going to teleport to A prime and get a reward of +10. And if I arrive in state B, I'm going to teleport to B prime and get a reward of 5. Now, under this, we can compute or just at this point have a look at what different value functions would look like under different policies. So if I just had a random policy, which just says I'm taking actions uniformly at random, I'm going to have a value function that looks like this. So this is giving me a value for each state, and visualized, I don't know, can you see that well enough? I mean, there isn't that much difference. You can see that there's higher value in the top states, and then the rest is largely flat because you're doing things at random. The odds of you ending up at the good states are fairly small. On the other hand, you might look at what the optimal policy might look like in this case. So if you had this value function, which I'm going to tell you is the optimal value function, and we could have the optimal policy, and I'll tell you how these are related later. So this tells you which the best direction to take in each step is. The visualization of this looks like this. So what this tells you is this gives you the value at each state, and all I need to do is, if I have that value function, I can act greedily with respect to that and just take the best action and just do essentially hill climbing. So from each state, I can say, just take a step in the most positive direction, because I already know I'm looking into the future. I'm already taking all possible outcomes into effect. Okay, so now I've introduced all sorts of cool ideas that are really important to be able to do reinforcement learning, but how do we do something useful with this? Vukosi is going to tell us about that.
Okay, we've got a lot of concepts through there. So we're going to go through a lot of math in the next few things, so just hold on. It's not bad. It is intuitive. And it sets up a lot of things that we're going to actually then talk about within reinforcement learning. So we talked about the value function, right, which again is the expected return, starting at a specific state S, and then and then following some policy pi. So what happens is that we can actually rewrite that earlier equation now to be recursive into this thing called the Bellman equation. In this equation, what you have is now that the value of your policy pi starting from state S is made up of what the immediate reward you would have gotten under that policy, and then if you have kind of the transition function, you can then recurse it on then all the possible next states that would have happened, and with that transition probability, and then just sum them up. So you can see now there's a v pi there, and now there's a v pi also that's connected to the next states that could then probably happen. So that's the immediate reward. This is going on for all the next possible states. Then we've got the probability of then reaching the next state, and then what that value of that all those next states would have been. Right. So now you can now view that in this way. So if you've then got this, where we were looking for a specific policy, we can actually then encode it for the optimal policy, where now we have V star. And what that means, instead of having the policy there, it's that we're always going to choose the action that leads to the highest next value, right? So now you have a max over there to take that best next possible action within that. So with this, though, we are now, all we have is the values of a state. And what is more intuitive if you're trying to figure out what is the best action to take in a state, right? That we want these policies. So to do that, we introduced then the action value function. So instead of just being V of S, now we have Q of S and A, right? Where you're saying, what's the value of me being in a state and then taking a specific action and then following some policy after that within that state. So now again, slight changes. We now have got Q S of A, but then now we've removed that pi within there. So it's no longer now given the policy. It's that first you're going to take the action A, and then from there follow pi, and that's what V of S prime is, right? You're just going to continue following the policy that you have, right? So in words, that's expected return starting at state S, first executing action A, and then following the policy pi for the rest of, infinite time, right? And now this answers the question: how good is action A under in state S under policy pi? And for that, it's now kind of easy to follow on that if you've got Q, the action value function, you can then also look at Q star. And Q star says what's the best action to take at a specific state, and given this, now you can actually then get the policy, right? That's where we've gone. Now we've gone from those action value functions, then we're looking at the optimal ones, and then now you can say that for each state, you would just choose the one that returns the highest action value function, and that's where now here you get that policy, right? And now finding V star or Q star then is equivalent to finding the optimal policy, right? That's what we are trying to do in reinforcement learning, is find from the information that you have, what's the best policy to take within there. And we can also say that every MDP has an optimal policy that you can find within this space, right? So given this formulation, how are you actually kind of going to learn this? So it's nice, I've given you some of the math in there, but then how are you actually going to learn these value functions so that we can then find this policy, right? So we're going to go back to that Bellman equation, and what this Bellman equation gives us, the optimal one, is what we have to do is solve this as a large system of value function equations, right? But challenge is that we have that max operator there, so it's nonlinear, right? As we're trying to solve it. But what we can do, because we have this nice recursion in there, is that we can actually try and look at it as being iterative, right? We can start and then update and update and update over and over again, right? So what are we trying to do here? We're trying to learn then how good the world is, and then we're looking perfectly into the future, right? We're always going to try and say, okay, given what we know right now, if we chose the best action, what would be the value? And then you keep on doing it over and over again and updating and updating and updating. So then what this brings us to then is dynamic programming, where we look at just a short algorithm called value iteration. And what we have here, just as a note, is that we have access to the full transition function. We have access to the full reward function, all states, and all actions. So that information is perfect, then we have it. So what we're going to do is we're going to then iteratively update V. So for each iteration I, you're going to go through all the states, all right? And you can initialize all of your V's to 0. And then what you're going to do then is for the next value of V, you're going to now do a one-step update, where you're going to say, I'm going to go through the transitions to all the next states, given that I'm starting at state S. Then I'm going to choose the best action given the previous value of V that I know of, right? And then the reason that it changes is that you also have this reward that's in there of saying, if you were to move from state S, giving action A to the next state, right? So you iteratively do this until some convergence, and then what you'll have inside there is the real optimal values of V, of the value function. But the problem, I think there was a question earlier, like, do we know all this information? The problem is that it requires you to have the full MDP within there. And in real circumstances, this is not something that you know within there. So in general, T and R, this full information is not something that we have access to, right? And as such, this is what brings us to looking at reinforcement learning through value-based methods. Okay. So in value-based method, what we're going to be doing, just to set up the scene for everybody, we don't have the transition functions, we don't have the transition model, we don't have the reward model. What we do have is access to some environment, right? So it could be a robot that has to move in this room. It has access to the room, and it can do things. And so we can experiment in there, or we can have access to some training data. We just put this in there because sometimes what you can get is just a batch of information about things that people have seen in the past, but in terms of moving around. So the goal then is to learn the value of states and the state actions. And then through that, remember, go and get what the optimal policy is supposed to be, so we can get that behavior. So, as I said, you don't have T and R, but instead, we're going to generate some samples. The way you do that is that now you can have some agent that wants to move around in this maze, right? So there it is. It then goes, OK, it's going to choose an action to say to move up, and then it moves to the next state, right? So there, what we got is the S, A, and S, right? S prime, which is the next state, and then it also then receives some reward in this state, and then it just gets a 0. Nothing is happening. But then that tuple is one experience that it can then use. We can then continue on there, and now it's in another state, chooses an action, but it actually can't move to that space, right? And then what it does is that it gets another reward, which is a -5, right? So all you're seeing is just those immediate rewards. You're not seeing what the long-term returns are. So that's the experience that you're then gathering as you're going through this. So one of the things that we're going to do if we're trying to kind of learn from experiences, how are we going to choose these actions that we're going to try, right? So that we can actually get our experience, because we have a lot of options that are available to us. So then this brings us now kind of trying to say, we're going to be learning. I haven't said yet how we're going to learn. We'll show you that. But we're going to be learning, and as we're learning, how do we choose the next actions to try out so that we can kind of either gain more experience or try to explore. So this brings us to kind of thinking about the bandit problem. So consider a row of one bandit machines, or slot machines. You have a lot of them that are available to you, and you can then pull on these arms, to see if you're going to win something or not in that space, or whatever that monetary value, right? And each of these bandits, we would say, then they generate some reward when you win and whatever value kind of it is. So now, how are you going to choose which machine to actually go and pull an arm on? Right? There's this question. So what you might do is you might go and then pull on one, get nothing, pull another one, get nothing, pull on the third one, and get something. Now you're stuck in this dilemma. Do you stay on that machine, or do you move to another one? Right? All right, so this is some of the things that happen during learning, in reinforcement learning, especially in these value-based ones, because you can do something, have some behavior, and then it actually gives you some reward. So now you're going to say, if you go back into that situation, do you choose that action that led to a reward that you've seen in the past, or do you try something else within that space? So this, what we call this, is the exploration versus exploitation dilemma, right? So here, in this trade-off, is that you want to maximize these expected returns, but then you have to balance between exploiting the knowledge that you have currently, so you want to be greedy, right? So take the best known action, but at the same time, if you've only seen very few things, you want to explore and see more of the world, because there might be something that then leads to even better returns in the long term. So you want to try something new. within that space. So to do this, I don't know why I did that. In our action selection strategies, as we're trying to now explore, go around the world, and as part of our learning, we're going to have some algorithm that helps us choose actions. So one way to do this, we have epsilon greedy algorithm. What it says, for some small number epsilon, for probability 1 minus epsilon, you're going to explore, right? So what this means is that for that time where you're actually going to explore, you can then choose your actions randomly, right? Right? But then with probability epsilon, you're going to always exploit the gain knowledge that you have, right? And epsilon is usually, I think this is kind of a mix. I don't think it's supposed to be that way. It's supposed to be epsilon, you explore, and then, yeah, sorry, those are supposed to be opposite. So it's supposed to be, with probability epsilon, you explore, and then with probability 1 minus epsilon, you're going to exploit. So that's why then usually epsilon will be higher at the beginning when you're trying to learn, and then over time, it will then go down, meaning that you are going to now exploit the knowledge that you've gained through the learning process within there. Right? The other option that you have after epsilon greedy is that you can use the softmax algorithm. So there is that if we've learned the Q value, which is the state action value, you can then come up with the the probability distribution over actions for a specific state given the softmax, right? And then you'll sample from that softmax in terms of what action you should be taking, and then you've got tau to control how much you care about the one that gives you the best state action value. Okay, so we've got now a way to choose actions in this world. So now we have to keep track of what we've learned, right? So we're going to be obviously we would have been moving around in the state and then doing things, getting rewards, bumping into things. What are we going to do? And in this case, we are going back to those value functions, right? We are going to use them to keep track of our experience. And then this brings us to temporal difference learning as a way. So now what we don't have is the transition model, and we don't have the reward model. Those have now out, but what we're going to do is learn from experience tuples, right? So here, you're going to initialize all the values for all the states that you have. As you can see, nice little pointer there. We don't have T, and then we don't have R, but we have S and A, right? And we're going to then go about our business, and then the policy pi could be E greedy, or it could be the softmax algorithm in terms of what we're going to try to learn, or it could be another policy that we already want to just evaluate how good that policy is. So the way that we're going to now update our value function, it's going to be on the previous value that we have for a specific state, and this term here at the back, at the end. And what it is that this is now the reward you would have gotten during that experience, the transition, plus then the discounted future value that you think the next state would have had. And this actually then gives you this estimate of how you think currently the state actually is, with just one step look ahead. But this then, for everybody here, given this week, should look familiar. It looks like an error, right? Which says, given this one-step look-ahead estimate and what actually we think the value of the state is, what's the error between those two, given that you have the immediate reward that you just got during the experience, and then this gives you the temporal difference error, right? And then you update your value that you have with a learning rate given that error. So what we did here is we only looked at kind of this one update. And we can even think about this, this one-step estimate. So this just, it's nice. You can keep on going, and then you will get to some value function, some good values for this policy. But we could actually then make these updates more efficient. So we're going to stay within there. All you've done is that you're now in your nice grid world, you've only done an update given that you've seen only one step. But then what if you see then a whole trajectory? How do you now update, right, the value functions of the beginning, given that now you've got more information about what's happened into the future? How do you go back and then update your initial, your initial estimate about the first state that you started on this trajectory on there? So this is where eligibility traces come in. So we're going to go back to that temporal difference algorithm and rewrite it, but now we're going to add a term here, E of S. Right, so these are eligibility traces. So this is TD0, which is exactly the temporal difference algorithm that I just showed you. And what happens is that now for each trajectory or episode, so you're going to have the multiple steps, you're really only going to keep track of only the one update over and over again. So you initialize all the E of S's for all the states that you have in your model to 0. And then for each tuple in a trajectory or an episode ends, and then you might start back somewhere else. You're going to then say, for the state I just visited, I'm going to say E of S is equals to E of S plus 1, right? And then I'm going to have this delta here, which is that error term that we had on the temporal difference algorithm, where it's for that one step, right? The error in estimates of the next, between the current immediate estimate and the previous estimate that we had for the state. And now for every state in S, we're going to go and update it given the alpha, you see, and the delta that's there that we saw before. And after that, and then here, if you look at this, in the first run of this, the only state that's going to be updated is the S that you saw during the experience tuple. Oh. Okay, so. Sure. So temporal difference learning is just a way for, it's a value-based method, meaning we're trying to keep track of the values of a state. So the temporal difference learning, so remember with the, with the value iteration, I'll go back just so that we can do this. It's going to be hard, but, okay. So this is the optimal value iteration. We had to have access to this T, which is the transition function. So now we're saying we want to learn from experience because we don't have that T anymore. So how can we still update the value function to get closer to what actually real V is supposed to be? Right? So what we use is this temporal difference learning. Right? And the temporal difference comes in right, because you're using this one step ahead. You've moved one step to the next time step, and then now you say, hey, here's what my estimated return would have been with the current reward that I got really from the environment, plus my estimate of what the discounted value of the next state would have been, minus what I think the value of state S would be. So that's the temporal difference there. That gives us the target that we're trying to, we want this to be as close to 0 as possible, right? And then we update the value given some scalar factor of this error, right? So that gives us, so we're still learning the value function, but now we don't have the transition function. We update it given our experience. Yeah? Okay. Yeah, okay. Yeah. Yeah. Yeah, so because you've got T and R, you've got a sum over all the possible next states. No. Oh, it was sum of next states, because you're going to choose. Yeah. Okay. It's okay. It's okay. Yeah. 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 Next state, right? Because you're in a specific state. Here, because the optimal one, you want to choose the best action, so that's why there's the max. But you're going to have a sum over all possible next states for every action. And because you have the transition function, it gives you a probability of transitioning from one state to the next. Yeah. Okay. Oh, because here we've got this kind of recursion, you're only looking at the next state. Right. Yeah, there we have. In reality, it's not, because even if we have, let's say this, you would say all the positions here are the next states. It's just that if you had your transition function, you can't go to all these other ones. So it will just be probability of 0 of going from this state here to there. You wouldn't, the only ones that would have is most like there and there. Yeah. No, like your transition function, it will encapsulate every next state you can go in, but only a few of them are possible. So everywhere else will be 0, because you can't transition there. Yeah, go. It's okay. Yeah. Thank you. One last question? Yeah. Okay. Yeah. Yes. Okay. So the reason we put the S prime in there, one, is that S prime, if it's deterministic, yes, your S and A will always go to the same state. If it's not deterministic, you might end up in a suite of next states, right? And then these will, so when you choose an S, you choose an A, you might get a reward. The reward might also not be deterministic. So, but then in an experience tuple, you've got a specific reward that you got, and then you got a specific next state that you experienced, right? So those are, like, and then those could be different for the same state and action choices. Yeah. 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 Okay, we'll just stay at optimal. Okay, no, so, yeah, so this is what you think the value of the current state is. This is what the one-step look-ahead value of that state is. It's what's the reward that you got right now, plus the discounted value given the next state of what you would have gotten. So this gives you like a V hat of S. Right? And you're saying, what's the difference between what I believe is supposed to be the value of the state and V hat, and that gives you the slight error within there. If you take this in expectation, like, over and over again, you want that to be close to 0 as possible. So the policy that you get your data from would be the one that you use. Remember, we said with V star, you can always find the best action given what you think is going to happen next from your value functions. So if you're you want to learn the optimal policy, you can put in like the epsilon greedy algorithm as the one that you use to actually go through and get these experience. So I think in the next bit, there'll be an example of a learning algorithm that does, and I think it will answer your question. You want to go, Mark? Yeah. No, I think it should get in. If your MDP, it might be a representation issue. If you can't get to, like you get some stationary point that just doesn't make any, it doesn't go to, yeah. So let me just try and finish this part. I think and then we can take some questions. Okay, so we said what we want to do now is think about doing updates, but then not just that one-step error, right, where we're just looking at that. So one of the ways you can do this is that we can look at the temporal difference learning that we just looked at simply as, like, here's a one-step rollout. You had a state, you chose some action and got a reward, and then you move to the next state. And that's what you've seen right now, and it's comfortable. Like, we know what that means. So now we can say, how do we still update the value of this state if we know that we've gone 2 transitions instead of 1? And how that changes, so there, you had a state, moved to S prime, you then did another action, and you moved to S prime prime. Right? And how that looks like, then it looks like that. Right? So you've got the reward that you got at the beginning, plus now the discounted next reward. Right? And then because you're going to discount again, you now have the square over that, because you were going to discount the second time, and now the value from S prime prime. Right. And then so this is still the estimate of the current state value, but now you've done a rollout of 2 steps instead of 1. And you can do the same thing now. We've got S prime prime, right, where now you can write it out like that, and then you do the update. This is still, again, the estimate the immediate estimate of how good V of S is supposed to be versus what we thought that V of S was supposed to be in our memory within there, and then that gives you kind of the complete error, and then you update given that error. So this then takes us to TD1 learning, where you want to keep keep information about all the traces. So now so we start off the same way. We're going to now, for the states that we see, we're going to put this +1 there, because the eligibility at the beginning is all 0. As we see a state given our S and SR and S prime, we just update it as saying we just seen the state. We calculate the delta here for the current state that we're in, And then for all the states that we have, we're going to do updates. But remember before we were setting it to 0 to get to TD0, where we would only update the state that we are currently in terms of the value. But then now here, we're going to have instead of setting it to 0 again and resetting it, we're going to have this gamma multiply by E of S. All right? Not to go too deeply in there, what it does is that when the next state, so you move to S prime, when you do the update, it adds that gamma multiply by R as part of the estimate to do the update of the previous state on there. So it gives us, well, if you can work it out, it will give you this update to V of S. It will actually add it in within there. And then it will just keep on decaying you haven't seen that state again, but it will keep on decaying as you go into that trajectory. And then when you start again, from a new trajectory, you reset everything to 0, and then you keep on going within there. Yeah. Yeah. Yeah, we're setting us up for this, right? But then now you say, okay, you've got now these two extremes, right, that you can have, where one, you're just doing one step, and the other one is you're keeping all of your history and updating the values given that history. Right, oh, I should have used that, but it was right there. And then this is now what takes us to TD lambda, right? And then TD lambda then allows you to also then control this decay rate. And what then that looks like ultimately is now you have this lambda value that then says how much do you care about keeping all the history, keeping all the history of your trajectory, or not only looking at one step, and then you can tune that to be kind of in between, and you can have kind of either faster convergence to the real value function, or slower, given how you deal with lambda. Okay, I think we can take a question. Yeah, 10 minutes. Okay, apparently it's supposed 10-minute break, and then we'll move on to the next part of the session. Okay. Yeah, thanks.
All right. Okay, let's get started. All hear me at the back? Cool. Okay, I hope you all acted optimally for the last 10 minutes or so. I know this is a lot of material. I know it's quite unfamiliar. Feel free to ask questions. I might have to cut you off for time reasons, but we're happy to chat about this afterwards as well. And hopefully when you see the next few versions of the same kind of ideas, you'll get the hang of it. Okay, so we can now learn stuff. That's awesome. What we're doing is we're trying to estimate this value function v from the experience of our agent moving around the environment. So just to clarify that point, the value iteration example Vukosi gave, in that stage, that was just to set up what the general problem looks like. But actually, in practice, we don't have those models most of the time. And we've got our agents just have to move around the environment and collect data to learn from that. The problem with learning using TD is that we're not using the actions at all. That's the first thing. And secondly, we'd actually rather learn this Q value function, this action value function. Because firstly, it's easier for policy extraction. Right? From the previous method, when we're learning the value of these different states, we still have to do a one-step look ahead to figure out which is the best action to take. We say, if I'm taking action 1, I would take a step that way. Let me check the value of that. If I take action 2, I'll move that way. Let me check the value of that, and then take the best one. We'd like that to be encoded directly in the value function. And then, yeah, so we don't have to do this look ahead. So this is going to take us to the next algorithm we're going to talk about, which is called SASA. And the reason for that is very deep and profound. It's because we've got a state and an action and a reward and another state and another action. Hey, look, it's an algorithm name. All right, so I'm going to talk about two other algorithms now, one being SASA, that use very similar principles to TD learning. And hopefully, once you've seen kind of 3 copies of the same ideas, you'll be more comfortable with the general concepts here. OK, this is what our algorithm is going to look like. And let's go through this. So remember, what we want to do is we want to have an agent moving around some environment, collecting samples. It's doing this exploration, exploitation trade-off thing. It's deciding to keep pulling the same bandit arm or trying another one. Or the other example I like is when you go to a restaurant. It's your favorite restaurant. The first time you went there, you had this dish, and it was the best thing you ever had. So every time you go back to the restaurant, you keep eating the same thing, but it might be the worst dish in the restaurant. So do you exploit your current knowledge, which is that that thing's amazing, or do you explore and try something else, right? So we need to be able to take actions in this setting. As our agent's moving around this environment, he's going to take these actions, sometimes from the policy, sometimes exploring. He's going to move to new states. He's going to receive rewards, and he needs to learn against this, right? So the point is, because he doesn't know these transition models, he doesn't know these reward models, he has to learn something, he has to learn this value function, and that lets him perform better in the future. All right, so the way we can think about this is for each episode, and again, the terminology here is that an episode refers to my agent starts off in its starting point, wanders around for a while, either succeeds, fails, times out, and then starts again, right? That's an episode. Now, each episode has multiple time steps, and those are your decision points. So during each episode, we're first going to initialize some state. That's where he starts off. He's going to pick some initial action from our Q value function using some sort of exploration, exploitation type method. And then for every step in this episode, while he's wandering around, he's going to take that action and see what happens. He gets some reward. The state of the environment changes. And he's going to choose a future action. So he's now got a new state. He's got state st plus 1. Now he wants to choose an action from that state that he could be executing. And using these 5 pieces of information, so the action he took from the state he was in, the reward he got, the next action he wants to take, and the next state he'll be in. So that's the kind of SARSA tuple. We're going to update the Q value function. Now again, this is a bit of a mouthful, well, eyeful, I guess. But it follows the same structure that we saw in TD learning, right? So we're updating Q of ST and AT. So we want to know, remember, we're trying to estimate how good is this action in this state when I'm thinking about the future. So we're doing an update. Now we're updating based on this term. And just to throw in there, there's a learning rate, which we haven't spoken about much, but this gives you an idea of the size of the update. Let's ignore it for now. And what we're going to look at is we're going to say, what is the value, what should the value of a state be? It should be the reward we get right now, plus whatever happens in the future. And that should be encoded by Q of the next state. Because remember, we want this to encode until the end of time, because we don't just want to act on this immediate piece of information. So we've got these 2 different terms that need to play a part in this. But we do discount the future, so we say that the thing that happens in a step's time is possibly worth slightly less to us. Gamma might be something like 0.9. And that is what the should be. Now, we do have a current estimate, and the current estimate is QST80. And so you can kind of think of it in this way, that if our current estimate was perfect, this term would cancel out in a sense, and we wouldn't need to do an update. Right? So we're trying to iteratively update our estimate of Q based on what's going to based on the reward we received and our estimate of what's happening into the future. Right? So it's the same concept that's happening in TD learning as well. Now, every time we receive this new sample, we're going to update this estimate. And the idea is if we leave our agent to play around in this environment for long enough, it should collect enough samples to learn good estimates of Q for every state and action pair. And we're going to use this to essentially take this do this planning, take this action in that state. So we're trying to learn that Q so that it gives us an idea of what the best action in that state is. All right. There we go. That would have been useful. All right, so the 3 key concepts here are you want to act in the environment. That's where you actually take the action and something happens. And hopefully you don't break your expensive robot. Then you want to do this look ahead and say, what might I be doing next time? And then you want to learn based on those 5 pieces of information you've got there. No more surprises. Good. OK. Now, we had to do this kind of looking forward 1 step. And that was to get this AT plus 1. That's what's going to happen at the next time step. And that was the next action that we're likely to take under this Q value function, right? And because we're doing that, this is what we call an on-policy algorithm, right? So it's learning from the thing it's going to do, right? So it's got one policy that it's learning against. But there's other things you can do. You can do an off-policy algorithm. Now, what this means is you don't necessarily need to be learning from the same policy. You don't need to be acting from the same policy that you're trying to learn. Now, the cool thing there is I might be trying to learn an optimal policy while taking some sort of exploration policy and trying different things. And I'd like it if these didn't have to be the same thing. There's other advantages to thinking about this off-policy instance, which is that I might want to reuse experience from, say, other policies in the same domain. I might have someone demonstrating trajectories to me. I'd like to be able to learn from all this experience and not just what my queue is going to do next, which was that key feature of SASA. So this gives us a different algorithm then, which is called queue learning. Is everyone somewhat happy so far? Cool. Okay. So queue learning is, again, a very similar idea, similar kind of algorithm with a minor tweak, right? We can look, it's the same kind of structure. We're initializing queue. We're going through multiple episodes. In each episode, this guy just teleports to his spawn location. That's the initialization. And then for each step in the episode, we're going to choose an action from that state in queue. We're going to take that action, see what happens, and we're going to learn. Now, you'll notice there isn't that look-ahead step. And the reason for this is, so we just have this act step and this learn step. Now, the important thing is, here is where the algorithm differs. And this is we're trying to take the best action for the next state, right? So we're not doing that lookup into our Q value function to say, what would we do in the next step? We're going to say, what's the best thing that we've seen so far that we could do in the next step? So we're trying to estimate the value of the state as being the reward I get right now, plus some discounted version of the best thing that I know so far I could do going forward. Now, this is where that difference is, because that best thing, some of that information might have come from a different policy that was exploring. It might have come from some demonstrations that you saw from something else moving around that space. But it means you're using this information more efficiently. And you don't have to do that extra look ahead. Is that difference clear there? So it's the exact same setting, we're just not having to do this look ahead, because we're now looking over the best thing we know about so far. Okay, I want to give a little demo if I can make the Mac work, which I'm bad at. Okay, so I want to show a little demo of what a Q learning agent would look like. So we've got this maze world that looks the same as the little Roomba cleaning the floor thing we showed you earlier. Now, in each case, what we're trying to visualize here is the Q values. So for each state represented by each square, we're going to divide them into these triangles that give you the value of each action in that state. So you can just think of, say, this triangle to the left tells you what's the value of that action in that state. And we're just going to play out what some of this learning looks like, just to get an idea of what happens with the learning agent. And did it start? Okay, so you can see as it moves around quite fast, so it starts off and it's doing a lot of exploration. It doesn't know anything. If you look at any one of these states, the actions all have 0 value there. So it's essentially you can't do any better than picking at random. But you can see as it gets to states that lead it somewhere good, it starts, in a sense, almost backpropagating the value into there. And you can see how that starts moving backwards. So it starts getting an idea in each state of some value. It's also learned that there's some bad ones around here. But as it does that, it's less and less likely to move into this part of the state space, right? Because now, firstly, you can decay the exploration, so do less of it. But if you're trying to act greedily and you're picking an action from your current state in your queue function, right, when you initialize, they're all 0. That doesn't tell you anything. But once you've done this many, many times, it starts giving you really good estimates, because we're trying to estimate from each one of these things, how good is it when you look at the future trajectories you could take from that state. Is that a question? Yeah. So in general, that's difficult. There are certain settings where you can do things with that, and there's a lot of active research on that. Your problem is that you can think of this fairly abstractly. You might have your state space is just a graph of states, and you might have that your actions are just random transitions between some of these states. And now, to actually say that in that general sense, to say, I took away one action which might have given me some distribution over 20 different states and replaced it with another one, it doesn't in general tell you anything about the other action. But there are ways of encoding this so that they can share information, or if you've got some other information that you can say that there's some mapping between them, then you can transfer information. Yeah. Exactly. And that's a limitation, is that what I'm talking about so far doesn't generalize, and I think that's one of the next points I'll talk about. Yeah. Sorry, to there? Oh, sure. Okay, so it's preferring the top path, and there's a couple of reasons for this. So the one is, obviously in the limit of infinite samples, it's going to get a perfect model of everything. We clearly don't have long enough to give it infinite samples, and so it's going to be biased towards things that it's taken. So if there's a number of trajectories and it happens to randomly discover one, it's more likely to exploit that because it can't exploit something it doesn't know. The other thing is if your actions are somewhat stochastic, it's riskier to take the trajectory around to the right, because there's some chance it could end up in the trap state that gives it a reward of -1. And so in expectation, it might want to rather take the slightly longer trajectory because that's safer, because actually under the reward function we're giving it, that's the optimal function to take. Okay, so yeah, you're right. This is going to take a long time to learn in general. And if you think about it, that makes sense, because for every state and action, especially the way we've encoded them here, just as discrete states and actions, where one doesn't tell you anything about another one, you have to try each action in each state several times to get a good estimate of its value. And so that does take a long time. But there's a lot of work and there's a lot of other methods and encodings that help speed that up. And we'll touch on a bit of that, but not a huge amount of that. But to some extent, if you don't know anything about the environment, if you don't know anything about the dynamics of the reward function, the best you can do is to explore. Yeah, actually that's right, yes. Yeah. Ever didn't you? No, because there's extra exploration that's happening in there. Yeah, I mean, so there's a lot of schemes for doing that kind of thing. We just gave you those two instances, epsilon greedy and softmax. But yeah, you could be doing something like that. So it's not necessarily taking the best thing. It might make a mistake in a sense there. And actually, that ties back to the next slide very well. Right, so there's this notion when you're doing this kind of research and running these kinds of experiments of these learning curves. And what that says is, how well does this algorithm perform over time with some number of episodes? So let me just set this up by saying this is a kind of grid world that has a cliff here. So you want to start off in that S state, you want to end at that G state, and navigate along that cliff. But if your actions are noisy somehow, then there's some risk of falling off the cliff as you're moving along. So just to look at that setup, these are what you would see as your standard learning curves when you run these algorithms. So you're going to run them for some number of episodes. Now, if you remember, at the beginning, this thing can't do anything other than act randomly, right? Because if it explores, it's random, and if it exploits, it's exploiting where it doesn't know anything. So usually we just set the exploration value really high at the beginning anyway, because that's what it's doing, and then decay it from there. Now, so what typically happens is it does badly at first. And this is quite a good one because it's quite a simple domain. And then the reward starts getting better. And if it's in this case where it only gets a reward for, let's say, a positive reward for reaching the goal and a negative reward for falling off the cliff, it's going to start, and probably in most episodes, if it hasn't learned much, it's going to fall into the cliff, right? That's something that fall off the cliff. That's something that it hasn't learned about yet, and I guess the cliff is closer to the start, and it's a bigger region of the state space, so it's more likely it's going to end up there. So it's going to be quite a while before it, through exploration, would discover the goal for the first time. And this is what's kind of reflected in these learning curves, that typically you start off doing really badly because you might be getting only zeros, or you might be only getting negative values. Those negative values might come from the actions that you take. And let's say that cliff wasn't there. You might still get a negative value. If you got -1 for every step, and your trajectory is timed out after 50 steps, then maybe after 50 steps of random exploration, you haven't even got anywhere near the goal. So maybe for your first few trajectories, you're just going to get -50 in that case. But over time, as you explore more and more, you realize that you're not getting any value from these things, and your trajectory starts exploring more of the space. At some point, it will get some positive reward, as we saw in that demo that we showed. And then once it's found a trajectory there, that's great, because now if it deviates from the trajectory and comes back somewhere, it can see, oh, there's a bit of value that's propagated its way back here, and it can follow that trajectory. And so once you found the goal the first time, it already starts getting a lot easier. And again, that's what you see in these curves, that they start off really bad and get better and better and better. And actually an interesting thing here is you can see that they both kind of converge. If you left them for long enough, they'd probably converge to the same thing, but with some exploration here, to answer your question from earlier, because SARSA is doing that one-step look ahead, which may have some randomness in it, it learns to be more conservative than Q-learning does. So although the optimal policy would be to just move right along the cliff edge, if there's some chance of you taking random action, if there's a higher chance of you taking random actions, you're more likely to take a safer path that's further away. Okay, so we had a question about generalizing, and that's a very good question. It motivates a lot of the research we do. So there's a lot of ways that you might want this to generalize. So the simplest thing would be, what about different tasks? What if instead of going to one location, I want to go to another location? But you might even care about different instances of the domain, moving your objects around, and all sorts of things like that. And something that might be really useful is to have some sort of a simulator so that we could ask questions about the domain, particularly if you've got a nice expensive robot or some self-driving car or something. You don't necessarily want all of this to be learning on the fly in the real world. And so it'd be useful to have some sort of model or simulator of this. And that lets you ask questions. You can start asking things about error bounds on certain concepts and so on. And to do this, we need a model, right? So we have to have some way of encoding what we think can happen in the world. Now, all the work we've discussed so far has been what we call model-free. Right? So we don't have an explicit model of these transition dynamics, and we don't have an explicit model of the reward function. We're rolling those both up into this value function. And if you remember from the equations I don't want to go back to now, that the propagation of value between states is a function of those two things, right? Because you want to say, what reward could I have gotten in that state, and what's the probability of having got there from the current state? So if we had this model, we could kind of explicitly compute that, but we could also compute other things that we wanted. right? So it's really useful to have a model in this setting. I'm just going to go into one model-based method, just to give you a taste for what it's all about. And just give you, yeah, just the general concepts behind this. Right, so as I say, what we want to do is learn a model, and that's T and R, which we want to learn from experience. Now, in some sense, what we were doing before, these previous algorithms were essentially running a control problem. So they were trying to figure out what the best action to take in each state was. In addition, they have to run a learning problem, which is to learn this V. In this case, what we want to do is learn R and T. So you can almost think of that as that could be a supervised learning problem, where you've got some number of instances of experience in the domain. So if I've been in this state and taken a certain action, over time I can learn what that distribution would look like. And yeah, we want this to be able to predict the next state and make comments on the uncertainty in the system. So just to give you the general setup here, in model-based reinforcement learning, we don't have a transition function, we don't have a reward function. As before, this agent's on its own in the big bad world. We've got access to the environment, which gives us some experience. But now what we want to do is try and learn these two models, and from those we'll compute a policy. All right, now you can think of it in the sense, let's say you're moving around your environment, and as before, you can be in a state, take an action, receive a reward, and transition to a new state. And this happens at every time step. Now, when you receive that experience tuple, several things can happen. And just to think intuitively of how one might learn a model here, what you could do is be tracking an estimate of your reward in that state and action. And you can do some sort of update with the learning rate, which just moves it towards R that you've just received. So again, it's a similar kind of format of update. You had a previous estimate, and we're trying to update it based on the error between that and the true reward you've just received. So that's how you could update your reward function. Similarly, you want to update your transition function. So you want to say that for this state action state tuple, I want to move it closer towards 1, which is 100% probability of that transition happening. And then for every other state that I could have reached from there, I want to move that closer to 0. Right? So that's kind of a normalization effect that says that by taking action A in this state, it made this particular transition more likely, which in turn made other transitions less likely. And finally, given that, I can just compute my Q value function. Right? So I can update that based on my new estimates of R and T, the same way we've seen before. Yeah. Right, so if you do have, so if you've got the exact T and R, we're in the same regime that we were right at the beginning with that value iteration, where you can just do a dynamic programming and pull out the policy from that. Well, pull out the value function from that and in turn get the policy from that. All right, so this is just intuitively how you might learn a model just as a frequency estimate of the transitions that you take. There's obviously more sophisticated things you can do here, but this just gives you a flavor for it. Something very simple. Now, one quite well-known algorithm in this space is called DynaQ. So this is based quite strongly on the idea of Q learning, which was the previous algorithm that I went through, with the idea that it's also going to learn a model. And I'm just going to kind of quickly step you through how this works. So at the beginning, again, you're in the same modality. You're running for some number of episodes. Each episode consists of a number of time steps. At each point, you're taking a decision. You're taking an action and moving between states. So we want to choose an action in a state from our current estimate of Q. And then we're going to do this, play the same game we always do. We take that action and see what happens. Having done that, we do our standard Q learning update. Right? So that's just basically Q learning over there. Nothing special. But now we've actually learned something more about the environment, so we can reflect that in our models. So given that tuple we've just seen, we can update our estimates of T and R using something like what I just showed you. And that means at the same time as us tracking Q, we can track the models of how the environment's evolving. Now, given an updated model, what you can then do is sample from this model So you can take a state you've seen before, so that's something you've got some experience about. You can take an action in that state that you've seen before, and you can sample some estimates of the model of what R and S prime would be, right? So remember here that the model is given by this T and R. And with those estimates, you can again update Q. So this is saying I've now got some better idea of what might happen in this context. I've learned something about it. Let me take some more samples to do this. Right, so now what we can do is we can update this model both from our actual experience as well as from our estimates of what we've seen. Now, obviously, this is more powerful if you've got a more powerful way of learning the model. So if a sample that you get can tell you something about the surrounding states, for example, then you're more likely to get better estimates about this. Right? So this just gives you some very basic idea of how you can use extra information to keep track of that model, which you can then do things like keep your Q functions updated even further from that. But actually, there's more reasons you might want to do something like this, right? So instead of just being able to plan with it, you can do other things. So we might have a lot of uncertainty in our model, and we typically do. And this comes from all the standard guilty parties, that you've got data sparsity, there's stochasticity in your domain, and there might be some fairly complicated structure that you don't have access to. And what you really might want to do is say that you can think of these blue and red as just different policies under some change of parameter. There might be some variance in the way that in the rewards you could be, in the returns, that's the total rewards you could be receiving under this policy. Now, if you wanted to actually evaluate a policy, you have to take that policy, plug it into your real world, and run it multiple times to start building these statistics. In many cases, that's expensive, right? Again, an expensive robot, you don't want to be running it into walls many times to see if anything changes. If you're trying to treat a patient, you don't want to try all these random drug combinations on them just to see what happens and what kind of variance you get. So it's nice to have a model to be able to make some estimates of these statistics. And typically, the kinds of things here you could do is the standard sampling you do anyways. You could do something like Monte Carlo sampling, which is just sample trajectories through your model and build these estimates of your probabilities. Okay, so now this seems like a lot of work. We've explained a couple different ways you can do things. You can try and learn your value functions directly, either V or Q. You can try and learn your models through T and R. What about just trying to directly learn the policy, which at the end of the day is the thing we care about? Right, we can learn a model, and then we can extract the value function, and from there we can extract the policy, and we showed you how all these things tie together. But yeah, that seems a lot of work. So what else can we do? Well, fortunately, there's another whole branch of reinforcement learning to deal with this. It's policy search methods. So again, I'm just going to give you a small taste for the kinds of methods that happen in this space and the way we go about thinking about these problems. So it's quite different to what we've described so far. And in this setting, again, we have the same fundamental setup where you don't know the models, either the transition or the reward models. Again, you've got access to the real world or some simulation of it, so I can take actions and see what happens. But I want to now learn the policy directly without all that extra gumph around the side. Okay, so as I said, this follows quite a different idea. Now in this case, because we care about the policy itself as an entity, we can try and parameterize that directly. So now instead of just saying that we care about some function over your states and actions, it can be parameterized by some set of parameters. Right? So that gives us some probability distribution of actions given not just your state, but your parameter values. This might look familiar to people that have been hanging out here for a few days. Right? So there's a few choices you can make for how this is done. You could do your standard things of having linear combinations of basis functions, whether it's a Taylor series or a Fourier series or something like that. You can encode specific state features that say something interesting about your environment, or you could encode this as a deep neural network, which ties back to everything else. And so the important thing here is that, again, you might have that your policy is now, I want to know what actions to take, given the state, which is some input, and the parameters, which might be, say, all the parameters or the weights of some neural network. And then this just becomes a case of finding the best values of theta, so your best parameters for this policy, and that's just an optimization problem. So under this setting, if there's some general form of function that describes our policies, if we just learn what this theta would be, That tells us everything we need to know. So, as again the last few days have spoken about, you need a cost function, or a loss function, or an error function, or something to learn against. So we can define this cost function, and there's tons of different ways you can do this. We often talk about looking at the starting value, so the value at the first state, or the value of the action in the first state. You can look at the average reward per time step over the entire trajectory you're executing. There's a lot of ways you might set up this cost function. Right? But then what you want to do is just find the parameter settings and maximize this. So you can do something as straightforward as gradient descent. And this is just on the policy gradient, the derivative of your policy with respect to your parameters. Right? So this should look very familiar to everyone. You can take a step in parameter space or weight space, just given by following the gradient there. Right? And that looks like all the neural net stuff we've been playing with so far. Now, why might you use policy gradient? Well, it works particularly well in continuous spaces, and as you can see, things that are parameterized in this way tend to work well continuously, and also in high-dimensional spaces, because you just need a nice function to do this encoding. There's also been a lot of great success recently in robotics, learning policies in this kind of way. So it's a very nice technique. It works really well. It's usually very efficient. Your two major downsides in this case is firstly that convergence isn't global, so you don't always learn the best possible policy, but you learn the best in some neighborhood of all the policies you could get. And that largely comes down to how you're doing the optimization step. The other problem is to do this policy evaluation, to evaluate the policy to find out essentially how good is it at each point. That can be quite expensive, and that can be quite high variance. So you might find that you have to execute this whole policy, do this whole rollout to actually sample the value at a particular configuration. Okay, so now we've spoken about 3 broad classes of methods. Again, we were just giving a taste for each one. And this gives you some idea of how they link together. So you've got your model-based methods, which you've got your states and actions, and you're trying to learn these models, these TNR, the transition and reward models, so that you can make predictions about S prime and R. Then you've got your function-based methods. And again, those are taking states and actions, and you're trying to learn a Q or a V, some sort of value function. And that because you want to get some estimate of A or the next state. And finally, you can do the policy search-based methods, where you're trying to directly learn the policy so that it spits out an action given the state that you're currently in. Excuse me? Under Q. No, you're trying to predict the best action to take there. Well, it's predicting the value, not the reward. It's not a model of the reward, it's a model of the value, which is the reward plus whatever happens into the future. So it's doing that look ahead into the future. Okay, now I think Vukosi should take over and tell us about another few interesting aspects of reinforcement learning.
We'll just kind of move towards finishing off, but I thought it would be interesting to talk about inverse reinforcement learning, connecting to what Benji talked about in terms of the problem with the Rats of Hanoi, that designing reward functions is kind of tricky within there. So in this time now, so designing reward functions is hard, and then often it's not clear what should be done or how it should be rewarded, and how do these actually reward kind of functions come from. So sometimes then we want to learn the incentives that explain observed behavior. So you might have some behavior that you want to see, so you can show somebody that behavior, and then you want to then figure out what were the incentives, what was the reward that led to that behavior, things, right? And then you can learn from an expert in this way, right? So in this setting, we don't observe the reward, but we want to learn it. So just to set it up, this is what we've been talking about for the first part of the lecture, and then in just the next few slides, we're going to, so where you get an environment, you've got the reward, and then you do reinforcement learning, and then you've got this policy and behavior that you want as an output. Inverse reinforcement learning, I don't know why it just went dark. You've got the environment, you've got the behavior, and then now you go into IRL, and then you get the reward. Right? That's where we're going with this. Right? So we've got a transition model. Right? You could have learned it through using a model-based way to collect the data. You've got no reward model. You observe the training, some data as A, as prime, and the goal is to then learn this reward model. So here's an example. You've got this nice grid world. We like grid worlds, which has water, and then you have a starting state at the top there, and you've got a goal state, and then you see somebody moving around and doing that. So just intuitively, what could be the behavior here? What's the incentives? How is the person? Okay, so then go into the water. Don't drown. Okay, so that's what you do. So you observe that trajectory, and now kind of, what was the goal of this agent? They wanted to get to the goal, but they didn't want to. So now it's like, how do you then learn a reward function for this? We don't have the reward function. We've just seen that behavior within. So I'm going to give a very simple algorithm, just the intuition of it, not all the details. It's a maximum likelihood inverse reinforcement learning algorithm, where what you're going to see is you're going to see those trajectories of somebody moving in this world. You're going to initialize some reward function within there. Then you're going to calculate the policy that would have come out of that reward function. Then you're going to take, hey, the policy that came from that reward function that I guessed first, what is the probability that the data that I'm observing would have been created by that policy? Right. After that, then you can then calculate a gradient, given that you know now what's the mismatch between the data that you observe and the policy that comes from the reward that you've guessed. And then through that, you would then update R towards it, and hopefully you should then get the policy. The reward should induce a policy that is closer to then recreating the data that you observe, and then that's one of the possible reward functions that actually come out of just observing that, and then you learn that that's the reward function. Right? So this is called the maximum likelihood inverse reinforcement learning algorithm within there. Then you can actually make these even more complicated. Right? So now you observe multiple traces that come from them, but then they have kind of different behavior. So for example, T1, again, you start somewhere in the gray area, you move around, that's a goal, and you can say, hey, T1 again doesn't want to drown, but wants to get to the goal. Red doesn't care, right? Can go through the water, they just need to get there fast. But there's also this yellow one here, which we don't know what it is. Is it just don't go through water, but it also seems to be don't hug or be near water, right? They had no choice here, but now you're trying not to actually get near. So if you have the opportunity, be as far away from water as possible. And in this case, you can just layer kind of your reward learning so that you then can actually then encapsulate things like multiple intentions and actually identifying different things in there. So why you would do inverse reinforcement learning? One is that you might have this problem that you're trying to induce some behavior, and then you want people to actually then give you samples so you can use it for crowdsourcing. Like you can say, hey, can you please show show a machine some examples of how you would solve X problem, and then from there you would then get the reward function that you need. Showing tasks to robots, where you just show it some behavior that you want to see, and then from there it actually learns that. And then also learning from experts, right? Or saying you see an expert doing something, and you say, how do I get the machine to actually have the same behavior? Inverse reinforcement learning can help you in that space. So, okay, the fun part of this presentation, just to end it off, was reinforcement learning is not just robotics and grid worlds and all those things. There's a lot of interesting work within the space, and we just wanted to highlight that, of saying the applications are kind of varied. So one of the areas is these randomized controlled trials. There's a lot of work by Susan Murphy, especially in, I think, it's SMART trials, sequential multiple assignment randomized trials, where you're going to have patients, you want to look at a new treatment or a couple of new treatments, and you're going to have this rollout that's going to happen, that people are going to be put on treatments, and you want to understand as quickly as possible, what the expected returns or the efficacy of those drugs are going to be. And it might be, then most of the time it's like 2 or 3 steps, not infinite, but it's being used in this space very well, and it's been very nice seeing biostats people coming into the reinforcement learning area. Advertising, I call it the collective tax we pay for being in machine learning. Is that there's going to be applications within there, but we can just skip to that and actually look at it from another way of saying, how then do you, if you're working on saying, I want to actually now use this to figure out a strategy to collect donations for some charity, right? So people do that, and the other one is collecting taxes. So the New York state actually has this. They've been working on this for years now. I think it's over 6 years, where what you want to do is people aren't paying their local rates and taxes, and you want to figure out what's the strategy that you're going to use to actually increase the chances that they will. And it actually becomes this MDP that they define, where you're going to start first and assess, and then go through all these multiple decision points. And what's interesting is actually the actions that they have. So like actions here could be contact the taxpayer by mail, by phone, create a warrant, a levy, income execution, or move it to different reporting areas in the city. I think at the initial one that I remember seeing on this, they had one even about the color of the color on the envelopes that should actually take that when you're sending mail. For example, if you live in an apartment building, your mail might go to one place and you go pick it out. So what they do is they send it in a red color so your neighbors know. But then you don't want to do that too early. You should actually, try figure out to do it, in a kind of considered way within there. So there's been a lot of work. I've actually been it's been interesting. How do you do this within there? Other work again from Susan Murphy. These mobile health interventions. So the one use case, you have a heart attack. One of the things about having a heart attack is afterwards, it's really great. The big thing is for you to stay active. It's not about going to gym, but just moving around. So what you might have is that you have a mobile phone, you've got one of these activity trackers, and then you have your phone also connected to some RL agent that then says, how do I learn how to send you interventions? So it might just be, hey, outside it's great, it has been, right? Maybe you can walk to work today instead of taking the car, just so that you can actually move around and then now learn what's the optimal policy for that specific person to get them to actually be active, right? It might just be, hey, during lunch, don't eat in the thing, walk to the park that's next to your office building or something like that, or walk up a flight of stairs to go pick up this instead of taking the elevator within there, and you're sending these small interventions on there. The other one, just to flash this out in terms of, again, the health application. Here, we're looking at HIV, chronic disease. You see a couple of patients that are going through treatments, and you see their responses. So here, it's the viral load, how many copies of HIV that you have. So you've got those are your features that you collect from a patient and also the disease, and then you encode some states. And then the actions are all these drug cocktails that are available to you to give to the patient. And it's important in HIV which sequence you actually give a patient, because the HIV actually mutates also given what you give the patient. So you don't want to give things that might actually then block off 90% of future treatments too early within there. So you have to then do it in kind of stages, and then the reward could be like this negated area under the curve. So you want to keep that as low as possible, and now you're going to learn over that data. So this kind of formulation allows you that you don't do experimentation on patients, but you can then look at past data and then try to actually then learn on top of that. And then you've got robotics, and there, as I said, we're learning behaviors of different things, and that's the PR2, and lots of different applications. And then games, as always, there's been a lot of work now on games, where there's Go, StarCraft, and a couple of other things. And automated trading is the same thing. You're trying to trade, but then you've got a long-term horizon and multiple decision points about buying and selling. You could also use kind of reinforceable learning within that space. So yeah, thank you.